Hello, it's Valentine from Simplistic, and in this problem we're going to take a look at a titration where we are given a sample, a 40 ml sample of zero point 0.1 molar nitrous acid. Now that's a weak acid, and it's titrated with a 0.200 molar solution of KOH. That's a strong base. So let's write that down really quickly. Strong base and weak acid. Okay, so whenever we have a titration between a weak acid and a strong base, typically what ends up happening is the base neutralizes the acid, and then once it's past the neutralization point, what happens is the weak acid ends up generating a conjugate base, which creates its own equilibrium. So as a result of that, we have to kind of look at the ice table from that and use that for our calculations at a later point in time. So let's go ahead and first take a look at the first part of the problem. Calculate the volume required to reach the equivalence point. Okay, so first of all, the equivalence point is the point where the number of moles of base is the same as the number of moles of acid. So what we need to understand is that the volume of the acid is not changing, but the volume of the base is changing. And since at the equivalence point, the moles of acid is equal to the moles of base, all we have to do is, step one is calculate the moles of acid using this information. So let's do that. So we'll write moles of the acid, which is HNO2, is given to us as, and that should be the molarity times the volume, which is equal to, molarity is 0.100 molar, and the volume is 40 ml, so that let's convert that into liters, so 0.0400 liters, and that is equal to 0.00400 moles. All right, so those number of moles should equal the same as the number of moles of KOH. Okay, so we can write moles of KOH is equal to 0.00400, which is the amount needed to neutralize the acid. And then since the concentration is already given to us, so let's write that as molarity is 0.200 molar. So to find the volume, we use this equation, this relationship. Number of moles is equal to molarity times the volume. So volume is equal to number of moles divided by the molarity. So to do that, we just write volume is equal to number of moles, that is 0.00400 moles divided by the molarity, which is 0.200 moles per liter, and that equals 0.0200 liters. So that is the volume. You can change that into milliliters. That would be 20.0 ml. So that's the amount of the volume of base needed to neutralize the acid, and that is what happens at the equivalence point. So that is the answer to part A. Now, and I shouldn't have written a B out here. Let's take a look at what happens in part B. They're asking what's the pH after adding 5 ml of KOH. All right. So the first thing we need to do is figure out how many moles does this 5 ml correspond to. So 5.0 ml of KOH is equal to, moles would be equal to volume, which is 0.00500 liters, times the molarity, which is 0.200 moles per liter, and that is equal to 0.00100 moles. Now we know that these many moles has been added. We have to figure out what the effect of these moles are. To do that, we have to do a little bit of a stoichiometric analysis, knowing well that if I take KOH and I react it with the acid HNO2, the KOH is going to neutralize the HNO2 and form water plus NO2 minus plus K plus. Okay, so what we're going to do is we're going to figure out the stoichiometry in this way. We're going to do before the addition, how much of each was there. Before the addition, there was obviously 0 KOH, but HNO2, we had how many moles of HNO2? We had 0.00400 moles of HNO2. So that is 0.00400 moles, and we had 0 and 0 of everything else. After addition, well, not after, so we'll add the after later on. We'll first write the addition. So when we added, what did we add? We added 5 ml, so that corresponded to 0.00100 moles. So that's 0.00100 moles. And then that, what happened after was the 0.0010 moles got consumed because all of this reacted with all of that. So after, we had 0 out here, but because all of this reacted with all of that, it neutralized this amount of acid. See, neutralized the same amount of acid, and therefore what we have left is 0.00300 moles. And from the neutralization of the acid, we should generate the same amount of conjugate base. So that should be 0.00100 moles. Okay, because this many moles of acid were neutralized, so that should be the same number of moles of conjugate base generated. All right, so once we have that, now all we have to do is to figure out the pH, we have to treat this as a buffer. So we write pH is equal to pKa plus log of, this is the Henderson-Hasselbalch equation, base over acid. pKa is given to us 3.34, right? So 3.34 plus log of the base would be 0.00100 over acid is going to be 0.00300. Now you might be wondering, why did we not convert these moles to concentrations first before putting it into the Henderson-Hasselbalch equation? And the reason for that is because if you convert this to concentration, you're going to divide it by a certain volume. So I'll just write that out. You divide it by a certain volume, which is actually the same volume that you have to divide the acid by. So when you actually take the ratio of these two, the volume terms cancel out. So we just are saving ourselves some work. We don't need to add the volume because they cancel out. Therefore, you can directly take the moles in this step and plug them in. All right. So once we know that, now we just have to kind of compute this, and this calculates to be 2.86. So that is the pH after addition of 5 ml of KOH. All right, time for part C. In part C, it's asking us what is the pH at 1/2 the equivalence point. So it turns out at 1/2 the equivalence point, what happens is half of the acid is left. And that half of the acid that was consumed, or basically, so the half that was consumed gave rise to 1/2 of conjugate base, which I'm going to call CB out here. So therefore, the ratio of the log, if we take the same term out here, Henderson-Hasselbalch equation, and put that out here, turns out the concentration of base is the same as the concentration of acid at the half equivalence point. Therefore, pH is equal to pKa plus log of 1 over 1, which is pKa plus log of 1, and log of 1 is 0. So the pH is equal to the pKa. So for part C, the pH is equal to 3.34, same as the pKa. And this is true for any buffer. At half equivalence point, the pH is always equal to the pKa. Okay. All right. Let's take a look at the last part, D. So in D, it says, what is the pH at the equivalence point? All right. So for the pH at the equivalence point, we need to understand that, let's write that down first, at equivalence point, what's exactly happening? Well, your base generated OH minus ions, and then you have the acid. And then what it does is you form water plus NO2 minus. Now before addition, we started off with 0.00400 moles of acid and nothing else. Okay, then we add, so at the equivalence point we should technically add the same amount of moles of base, so that should be 0.00400. So after, what's going to happen is this base is going to neutralize this acid, which means you're going to have 0 OH minus left, and when it neutralizes that acid, you're going to have 0 acid left. Okay, and then turns out the acid is going to generate the same amount of conjugate base. So really at the end you're going to have 0.00400 moles of conjugate base left over. So as we mentioned right at the beginning of this video, the conjugate base is now, because that's a weak conjugate base, and it's generated from a weak acid, that conjugate base is going to have its own equilibrium set up. So we have to draw out the equilibrium for the conjugate base. So we write NO2 minus plus H2O, which gives us HNO2 plus OH minus. Okay, and then we have to create an ice table for this. So initially we have, first of all, we have to convert those moles to concentrations to be able to plug it into an ice table. So to convert the moles to concentration, we'll just take this number out here, and we have to divide that number by the volume, the total volume. So the total volume, we already calculated the volume of base right at the beginning, needed at equivalence point, that was 20 ml, and the volume of acid we have is 40 ml, so that's 60 ml. So out here that should be 0.0600 liters, and that gives me a number of 0.0667 molar. That's my concentration. So let's put that in out here, 0.0667 molar. Initial change is going to be minus x, and then we have x and x out here, and at equilibrium we have 0.0667 minus x, and then we have x and x. Okay, now since this is the equilibrium for a base, NO2 minus, so its Kb is equal to x squared over 0.667 minus x. Okay. Now, but the Kb is not given to us. Let's take a look at what is given to us. Okay. What is given to us is the pKa. What that means is we have to use the pKa to solve for the Ka, and then use the Ka to solve for, and then use the Ka to solve for the Kb. Now, I can do it, that's one way to do it. Another way to do it is, we can, since the pKa is given to us, we'll use this relationship, pKa plus pKb is equal to 14.00. So 3.34 is the pKa given to us. Let's solve for the pKb. So pKb is equal to 10.66. Now if we take pKb, 10 is equal to negative log of the Kb. Therefore Kb is equal to 10 raised to minus 10.66, which is equal to 2.187 times 10 to the negative 11. Okay, so we'll just take this value out here and plonk that down here and solve. So we'll assume x is negligible out here. So then this becomes x squared over 0.667. I'm sorry, that should be a 0.0667. All right, so once we have that, Then x squared is equal to, we multiply those terms out and then solve for x. So essentially what we're doing is we take this term, we multiply it with this term, and then take the square root of that product. So we get x is equal to 1.207 times 10 to the negative 6 molar. Okay, so now to find this is the concentration of HNO2 as well as OH minus at equilibrium. But since we're interested in the pH, so all we're going to do is we're going to take the negative log of the OH minus concentration, which is going to be negative log of 1.207 times 10 to the negative 6, which is equal to 5.92. And that is the same as the pOH. And therefore pH is equal to 14.00 minus 5.92, which is 8.08. And that's the pH after addition, that's the pH at the equivalence point. Now, isn't it interesting that you have the same number of moles of acid and same number of moles of base, and you're expecting the pH to be 7, but it's not. It's a little greater than 7. That's what happens when you titrate with a weak acid and a strong base. And the same thing happens when you titrate with a strong acid and a weak base. Okay, the only time at the pH is 7 at equivalence point is when your acid and base are both strong. All right, I hope that made sense. Thank you for watching.